Okay, first I will draw a simply supported beam. It need not necessarily be a simply supported beam. It can even be a cantilever beam. But I will just draw a simply supported beam. If you want to try for cantilever beam, that's perfectly fine. Let me define the geometric properties of this simply supported beam. The simply supported beam has got a length of magnitude L. It has got a moment of inertia of magnitude I. I is resistance to bending. Greater the moment of inertia, greater the resistance to bending. Now, what is the stuff that this beam is being subjected to? This beam is subjected to a uniformly distributed load. So, what is the rate of loading? The rate of loading value can be Q. So this is the uniformly distributed load that is acting on this simply supported beam. And the rate of loading is Q. It can be Q newtons per meter, or it can be Q newton per mm. So the rate of loading in general, let us say that it is Q newtons per meter. It can also be written in Q newton per mm. What is the material property? This beam is made up of material that has got an Young's modulus value of magnitude capital E. Now, I'm going to localize my attention on this small portion of this beam. Let us say that the length of this small portion is dx. And I have considered the small portion at a distance of x from the left-hand side. So the small portion is considered at a distance of x from the left-hand side. So this is the small portion that is under investigation. So this is the small portion that is under investigation. So the small portion that is under investigation. Okay, now I'm going to represent the way in which the beam bends. So this is a highly exaggerated view. So let us say that the beam bends in this fashion. Because of the load that is acting, let us say that the beam bends in this fashion. Now you look at this particular portion. This particular portion has got bent in this fashion. So what I'm going to do is I'm going to draw a highly exaggerated, augmented and amplified view of this portion which has got bent in this fashion, and I'm going to represent the highly augmented and amplified view. So this is the small portion. So it is like an arc. Let us say that this arc has got points A. I will call this point A, and I'm going to call this point as B. What I'm going to do is I'm going to entail a set of coordinate axes. So this is going to be our y-axis. This is going to be our x-axis. So you see x and y are our reference frame now. So this arc represents this portion, and it is a highly exaggerated view. Since this is an arc, it should have a center. Let me call this center here as O. And let me join the points O and A. And let me join the point O and B in such a way that they are making a small angle. So the angle, the subtending angle here is d psi. What I'm going to do is I'm going to draw a horizontal from the point A, and I'm going to drop a vertical from the point B until they meet at the point C. Let me call this angle psi. Now what I'm going to do is, first I will localize my attention on this triangle here. It is not, strictly speaking, it is a triangle. It is not a triangle because this is an arc. We cannot assume that as a triangle, but we can do that without incurring any serious error in mathematics. So if you can assume this arc to be a straight line, you can still do the calculations without incurring any serious error in mathematics. So it is an assumption that it is this ABC is the triangle. So first I will localize my attention on this triangle ABC. Then I will localize my attention on this sector OAB. So first I will concentrate my attention on this triangle. Later on I'm going to concentrate on this arc OAB. OAB. Now in this triangle ABC, if this is the angle psi, I will call this BC as dy, because y is being measured in this direction, and I will call this AC as dx, a small distance dx, and I will call this arc distance AB as ds. Now what I'm going to do is, in this triangle ABC, it is easy now. Can you just tell me what is sine psi? Well, it is opposite side divided by hypotenuse. Opposite side is BC, which is dy, and hypotenuse side is ds. And in this triangle ABC, can you just tell me what is cos psi? Cos psi is adjacent side, which is AC, which is dx, divided by hypotenuse, which is AB, which is ds. Can you tell me what is tan psi in this triangle ABC, which is opposite side, which is dy, divided by adjacent side, which is dx. You may call this equation as equation number 1. You may call this equation as equation number 2. You can call this equation as equation number 3. What I'm going to do is, I'm going to concentrate on the third equation here. Differentiate equation 3. So just go ahead and differentiate this equation 3. Let us see what comes out of that equation. If you differentiate equation 3, what is differentiation of tan psi? With respect to x, of course. Differentiation of tan psi is secant square psi. Since you are differentiating with respect to x, it is secant squared psi into d psi by dx. And if you differentiate this dy by dx with respect to x, what you are going to get is d squared y by dx squared. Now tell me, what is d psi by dx? D psi by dx should be equal to d squared y by dx squared whole divided by secant square psi. So that is the equation that we are getting from equation 3. If you differentiate equation 3, maybe I will call this as equation number 4. Okay, now let me concentrate on this arc OAB. If you look at this arc OAB, this distance OA and OB should be the radius. Now, what is this arc distance? ds, I will write that here. ds is equal to, this arc distance here is given by r into this subtended angle d psi. So arc distance ds is equal to r into d psi. So that is the arc distance. Now in this equation, what is 1 by r? 1 by r is equal to d psi divided by ds. That is what you will be getting if you take this r over here. You will getting 1 by r, and you take this ds over here. So 1 by r is equal to d psi divided by ds. Now in this equation, 1 by r is equal to d psi divided by ds. I'm going to divide the numerator by dx, and I'm going to divide the denominator by dx, so that I do no damage to this equation. If you look at this numerator, immediately you can tell that d psi by dx is same as here. So you can take this value and you can put it here. So d psi by dx, you can take this value and you can just put it here. And what is ds by dx? Well, if you look at equation number 2, ds by dx is just the inverse of equation 2. So ds by dx is 1 by cos psi, that is going to be secant psi. So in this equation, d psi by dx, take it, d squared y by dx squared whole divided by secant square sine whole divided by ds by dx is simply secant sine. So in the next step, 1 by r is equal to d squared y by dx square whole divided by secant squared psi into secant psi, that becomes secant cube psi. I can write this as d squared y by dx square whole divided by secant square psi whole to the power raised to the power 3 by 2. So if you bring this 3 by 2 over here, this 2 and 2 goes away, you will be left with secant cube psi. So essentially they are the same. The reason why we write this particular equation in this form is you can write the secant squared psi as 1 minus tan squared psi. So that is the reason. So I'm sorry, it is 1 plus tan squared psi. So you can write this 1 by r is equal to d squared y by dx squared. The secant squared psi can be written as 1 plus tan square psi. So secant squared psi minus tan squared psi is equal to 1. So you work out for secant squared psi, that becomes 1 plus tan squared psi raised to the power 3 by 2. I have to tell you that this value tan squared psi, for very small angles of psi, for all practical purposes, the value of psi is going to be very small. So psi is very small, it is vanishingly small. So since it is vanishingly small, you can neglect this value. So it becomes 0. So all you will be left with is d squared y by dx squared. So I have got the value of 1 by r now, which is d squared y by dx squared. Okay, now we have got the value of 1 by r. So 1 by r is equal to d squared y by dx squared. So that is the value that we have got. Now what I'm going to do is I'm going to find the bending moment right at this small portion. It is very small, so I will just discern a section here. Let us say that it is a section XX, and I'm going to find the moment of all the forces about this section XX acting on the left hand side. So let me find the moment. In order to find the moment, first I need to find the reactions at these 2 points. So since it is a symmetrical load, the rate of loading is Q, so the total load that is acting on this particular beam, that is going to be Q into L. So this is the total load. Since the loading is perfectly symmetrical, half of the load is acting on the support here, so it is going to be QL over 2. And half the load is acting on the support here, that is QL over 2. And what is bending moment about the section XX? Well, you can either consider the total load that is acting on the left hand side about this section XX, or you can consider the total load that is acting on the right hand side about the section XX. So I will just consider the total load that is acting on the left hand side of this section XX. And the moment of this load about the section XX, that is going to be force into perpendicular distance. That is by definition, the definition for moment, it is force into perpendicular distance. So force is QL by 2 and perpendicular distance is x. So moment about the section XX is equal to force, which is QL by 2, and into perpendicular distance, that is going to be x. And I'm going to put a plus sign here. The reason why I put a plus sign is because it causes a clockwise moment. And what is the moment of this UDL? Well, this UDL is causing an anti-clockwise moment, so I'm going to put a minus sign here. Moment is force into perpendicular distance. What is the total force that is acting from this point? Maybe you can call this point as A. From the point A to the section XX. The total force is Q into X. That is the total force. Q Newton is acting over 1 meter. So for X meters, the total load should be Q into X. So the total load is Q into X. For UDL, you make an assumption that the total load is assumed to be concentrated at the center of A and X. That is the assumption that you make. So the total load is assumed to be concentrated at the center of A and X. So that is at the center here. So the perpendicular distance from the center to the section XX, that is x over 2. It is simple. The total distance is x. Half that distance is x over 2. The reason is because the total load is assumed to be concentrated at the center. So the perpendicular distance is x over 2. So that should give us the equation for moment. So moment is equal to qlx over 2 minus q into x squared over 2. That is the equation for moment. I'll just put a nice box here. And I'll also put a box for this equation. By this time, you would have guessed why I need to get an equation for 1 by r and why I need to get an equation for m. The reason is simple. You know the bending equation that you learned in your strength of materials, that is m by I is equal to sigma by y is equal to E over R. And I'm going to concentrate on the first part, and I'm going to relate it with the third part. So what I will be getting is m by I is equal to E by R. Now I can tell you that m into R is equal to E into I. You see, I can take this equation and I can substitute the value of 1 by R in this particular equation, and I can take this value of m and I can put it over here. Let me see what comes out if I substitute this value. So this term should give the flexural rigidity here. Again, it is something that is analogous to resistance to bending. And you see that the flexural rigidity is a function of the product of, is directly depending on the product of moment and the radius of curvature. Okay, for a given load. So I'll just take this value of 1 by R and m and I will just substitute it over here. Let me see what comes out. M is q L x over 2 minus q x squared over 2, that is m, by I. So I will just put 1 by I here, is equal to E into 1 by R. So I got the value of 1 by R, which is here. It is d squared y by dx squared. So that is d squared y by dx squared. Maybe I can take this I and I can put it over here. So what is that I will be getting? So qlx over 2 minus qx squared over 2 is equal to ei into d squared y by dx squared. What I'm going to do is I'm going to differentiate this equation 2 times. If I differentiate this equation 2 times, one time differentiation, this term just vanishes, it goes to 0 if we differentiate that twice. This term, so this term goes to 0 after differentiating it twice. And what happens to this term? This term, if you differentiate 1 times, you get 2qx, so 2 goes away. If you differentiate 2 times, you just get q. So after differentiating, this term is going to give you the value as q. Well, there is a negative sign. You can put a negative sign there. Into ei into d raised to the power 4v, d power 4v by dx raised to the power 4. I can rearrange this equation as ei into d power 4 v by dx power 4 plus q is equal to 0. So that is the governing differential equation of a simply supported beam that is subjected to area. Now the big question is, why do you want to derive this equation? So after solving this equation, you know, when you solve the differential equation, you get this dependent variable v. Here v here stands for the displacement, vertical displacement. I'm sorry to use the notation v because all of a sudden I have changed the notation from y to v. There is a reason, because already in the bending equation you have this notation y. So sometimes it may be confusing. Y here actually stands for the distance from the neutral axis to the outermost layer. So you should be able to differentiate the y in this equation from the y in this equation. Here y is the distance from the neutral axis to the outermost layer. Here y represents the vertical deflection. So you may want to use the notation v instead of y, just to avoid confusion. So you want to find out this deflection, vertical deflection. Now why do you want to find the vertical deflection? Because if you know the vertical deflection v or y, vertical deflection, there is a relationship between vertical deflection and bending moment. And there is a relationship between bending moment and bending stress. So from vertical deflection you can find the value of bending moment. From bending moment you can actually find the bending stress. So once you know the value of stress, you can take some smart, tangible engineering decisions. You can tell whether the beam is going to fail or not for the given load. So that is the whole idea.